Hello, I'm Johnathan Harter. I work for ZOS Comm Server Organization in VTAM. I've been working in VTAM for the past 22 years in various incantations. I've done design, development, test, and change team and level 2 support also. I'm going to be presenting a series of APPN topics for everyone to use as educational material.
The topic that I'll be discussing today is called A Practical Guide to Optimizing APPN and EBN or Extended Border Node Searches. This is a two-part presentation that I normally give at Share that I will be giving in one very long excerpt right now. As a quick summary of the agenda, the first topic that I would like to discuss is searching using an alias name as opposed to a network qualified name, what the implications are for that and what the tuning configuration implications are for that. The second topic I would like to discuss is who is my network node server, so that we can identify who the network node server of any given resource in the network is. The third topic discusses subarea searching, how they're performed, and how to tune them, the best practices probably for tuning subarea network searches, including the controls and also a sample adjacent SSCP table that we can use for a subarea to APPN migration. The fourth topic that I'll be discussing is tuning APPN border node searching. Most of APPN searching really does not require any tuning, but there are some tuning knobs that you can use when you're doing border node searching controls. So I will be discussing those. I'll talk about what border nodes are. I'll talk about the controls that you have for APPN border nodes. We'll talk about subnetwork routing lists, and then we'll also talk about these adjacent cluster tables that you define in order to optimize your EBN searching. And finally, at the end, I've got some debugging aids that you can use to help diagnose problems involved with searching in a mixed APPN subarea and a border node environment. So the first subject here is searching using an alias name. So why should we avoid searching using an alias name? The reason we should avoid searching using an alias name is because if you don't know what the net ID is of the target resource, then you pretty much have to search the entire world in order to find it, because you can't really control searching in just one direction. You're not exactly sure what direction you should be searching in. Again, an alias name is an 8-character name that you provide to start a session with a partner's LU. And the net ID is not provided, so we're not sure what the target net ID is. Instead, as part of our searching algorithm, or maybe as part of predefining cross-domain resources, or maybe as part of exit routines, you can actually translate the alias name into a real LU name, and that means network qualified. And then you can do all of your searching based on the net ID of the target resource, which generally gives you a good feel of what direction you should be searching. The default adjacent SSCP table is the one that you would use for searching when you're not sure of the net ID. Typically, you can define adjacent SSCP tables by net ID and also by owning CDRM. But if you're not sure what net ID is, you're going to have to pretty much search everywhere. So your default adjacent SSCP and or your default adjacent cluster table would be used for all alias searching. And therefore, you would have to typically define an adjacent SSCP or an adjacent cluster table that searches the entire world in order to be able to find the resource, in order to guarantee that you can find the resource. Right? And keep in mind that if you're searching with an alias name, if you're using border node dynamics equals limited and it's an alias name you're searching for, that actually works a lot like, in fact exactly like border node dynamics equals full, which we will talk about in a few more charts later. The performance problems that can result from alias searching are the fact that you're sending the search everywhere in the world. You may send it into adjacent customers, and they should not be bothered by this search because the target resource definitely does not reside there. You could do a lot of extraneous SNI searching, EBN searching. You might even broadcast your own network when you didn't really want to do that. So there are lots of performance implications for alias searches. It's not just when you kick off the search either. It's possible that an adjacent customer is kicking off the search, and when the adjacent customer kicks off the search and sends it into your network, once it's in your network, you're basically handling an alias search as well. So regardless of whether the search starts in your network or in an adjacent network, once the alias search reaches your network, there are implications on how your network will search based on that alias name. The way you prevent alias name searching is by converting the alias name to a network qualified real name. And as I mentioned a little bit earlier, there are several ways to do that. The first way to do it is by using the alias translation function of the session management exit. That's a routine that you would write and activate on VTAM. And every time a request came in with an unqualified name, we would drive this exit and let you fully qualify the name for us, and possibly even change the name of the LU if it's truly an alias name. If the alias name, that is not the same as the LU's real name. You can also use the NetView alias translation application to do effectively the same thing. This time we actually drive a NetView function with the alias name and allow the NetView alias translation application to return the fully qualified LU name with the net ID, that is. And if it was different than the LU name, of course, it would provide the translated LU name as well from the alias name. The third way to do this is with predefined cross-domain resources, or CDRCs. If you predefine cross-domain resources, you can predefine them with a net ID. And when VTAM adds these to the SRT table, we always add them by their real net ID as well as by the local net ID in case he's cross-network. And what that means is that if an alias request comes in, we'll look it up as an alias name using our net ID, and we'll find the predefined cross-domain resource, but then we'll look at it a little bit more closely and realize, oh, this was predefined with a different net ID, so this must be a resource that's in a different network. And we actually know the real net ID right away without doing any more lookups. This only works if the alias name, the 8-character LU name that you're using for an alias name, is the same LU name that is his real name. All right? If you're using, for example, if you're using an alias name called KixB to represent a resource in NetB that's called Kix, not KixB, then the alias name is KixB, the real name is Kix, and they really represent the same resource. That's an example where alias translation would be required, and you would not be able to use a predefined CDRC for that. Predefined CDRCs, again, are only, they only work well when the alias name and the real name are the same 8 characters. Now in ZOS V1R8, ZOS COM Server version 1 release 8, we actually implemented some an alias search operand that you can use to actually help prevent alias searches from entering your network. It's called alias search equals yes or no. You can code it on ADJSSCP definitions that represent nodes that are in a different network than you. So they have to be on the other side of a border node boundary basically from you. And if you code alias search equals no, which happens to be the default, then any search coming in from that adjacent node is allowed to come into your network, whether it's an alias or a real name. If you code alias search, excuse me, that was alias search equals yes, which is the default value. If you code alias search equals no, which means I don't want to allow alias searches, then if the adjacent node tries to send an alias search into your network through this node, then we will reject it immediately with a special sense code saying we're only allowed to receive network qualified names from you. And now the idea is that the adjacent customer has to make sure that he has tuned his searching correctly so that only network qualified searches make it into your network, preferably with the correct net ID. And that way when the research request makes it to your network, you can use customized ADJSSCP tables and adjacent cluster tables to optimize the searching for that resource. That was all added in V1R8, and you can do that on an adjacent non-native node basis. So some nodes that you might consider trusted, you might allow alias searches to come in, like your test network. Other nodes that you don't trust, for example, adjacent customers who have not tuned their network well, you may want to code alias search equals no on the definitions for their adjacent nodes so that they are required to send in fully qualified searches rather than alias name searches. We also added another option on the ADJCLUST definition in ZOS COM Server V1R10 called auth-nets for authorized net IDs. And this is a way for you to specify that when the adjacent node sends a search request into your network with a network qualified target resource name, the net ID of that target resource must match one of the net IDs coded on the auth-nets operand, or else you will reject the search immediately again, just as if an alias search had been received with alias search equals no. In this case, auth-nets can have up to 256 different net IDs that you can code on there, so that you're allowed to accept searches for those target net IDs from this adjacent node. And of course, just as with the alias search, you can code auth-nets differently on each ADJSSCP definition that represents an adjacent non-native node. All right, auth-nets equals net A indicates one authorized net ID is allowed. Auth-nets equals net A, B, or C indicates that 3 different target net IDs are allowed. Auth-nets equals, without anything afterwards, means that no net IDs are allowed, which means we will not accept network qualified searches from this node. The bottom flavor here, in conjunction with alias search equals no, would actually have the side effect of not allowing any search at all to come in from the adjacent node. You would still be allowed to send searches out to him. He would not be able to start searches inbound. That may or may not be practical, but nonetheless, that's the way it would work. So now we'll talk a little bit about how alias translation actually is performed. We're talking about the alias translation application or the session management exit application in this case, because both of those functions run on the subarea side of VTAM. And as a result of that, you can only drive these functions when the search request actually makes it to the subarray side of this VTAM. Now, the first example I've shown up here is a pure subarea network, where we've got a data host in our network attached to our CMC, and the CMC has an SNI connection over to another CMC over in the NetZ network. Alias translation in this case could be done at any one of the hosts because this is a pure subarea network, and so the subarea side of each of these VTAMs would certainly be involved in the session setup process. But most customers don't run the the alias translation function on the data host. Instead, they will only run the function on the CMC. The idea is that data hosts are typically required to send the search to their CMCs first to see where they are, and once the search request reaches the CMC would drive the NetView alias or the alias translation application, whether it's NetView or SME, and it would resolve the unqualified name to a fully qualified name, and then from there, the CMC would be able to do all of his searching using the fully qualified name. In this case, if it mapped to a NetZ target resource, then he would presumably pick an ADJSSCP table that maps to the correct paths or the optimized paths to get to the NetZ network. The next example that I'm going to show you shows that we've migrated our network from subarea to APPN, but the connection to our adjacent customer network Z is still a subarea connection. Typically when we migrate to APPN, the data host would become endnodes, which I show in green, and the network nodes, the CMC would become an APPN network node, which I show in red. And notice that the subarea nodes I'm showing in blue, just for color coding information. All right, so in this case here, if the end node, just like the data host, sent an unqualified, an alias search into the network node, before he searched the subarea side and the subarea network and searched into network Z, the subarea side of the network node or the interchange node would actually get control, and he would be able to translate that alias name to a real name before he performs the subarea search. The problem, of course, is that this interchange node may also be a border node, and if he is a border node, when the search request comes in from the end node, it actually comes into the APPN side. And so the adjacent cluster table or the border node searching would typically be done first. And we have not translated the alias name to a real name yet, so all of the APPN border node searching in this case would be done using the alias name. Once we gave up on that, we would send the search over to the subarea side of the interchange node. He would fully qualify the search, and then he would be able to search the subarea network using the fully qualified name. But again, in this case, the subarea searching works fine, but the APPN searching does not necessarily work as well. And in this case, the APPN searching would have been performed first, and so you may incur a lot of overhead before you get to the optimized searching on the subarea side. The final case is where we have migrated our SNI connection to an APPN border node connection. And now, when the search request comes in from the end node to the interchange node, or the border node here, A1, and the border node forwards it out into network Z. In this case now, the search request is coming into the APPN side of A1, and it's also leaving the APPN side of A1. So in this case, the subarea side of A1 was never given control of the search, and because that's where the translation function occurs, we never had a chance to translate this one. So the idea in this case now is that we never had the opportunity to translate the alias name to a real name before we actually did it, before we actually did the searching. So this is a case where alias name translation, either via NetView or via the session management exit, does not really help you in optimizing the search performance. So the second way that we talked about for translating alias names to real names is by predefining cross-domain resources. I talk here on this chart about strategies that customers might use for predefining cross-domain resources. The obvious method is that you predefine every resource in the network as a cross-domain resource with a net ID. And by predefining everything, you don't really need a default adjacent SSCP or a default adjacent cluster table to use. That is, of course, assuming that you have predefined adjacent SSCP tables and adjacent cluster tables for every valid net ID that you might be searching for. Since we always have a network ID specific table to use, and since all of our searches should be network qualified, then we typically would be able to pick the best table and always search that way. But trying to keep track of every resource in the network, both your network and in adjacent customer networks that you need to keep track of, trying to keep track of them all can be an administrative nightmare. Every time a new resource gets added, you have to add a new cross-domain resource definition. Every time something goes away, if you're cleaning things up correctly, you would want to delete the cross-domain resource definition. So most customers are not willing to predefine all resources as cross-domain resources. So instead, the strategy that I suggest is that you predefine all the cross-domain resources that represent resources in other networks. So predefine all the cross-network resources and predefine them with a net ID. If you predefine all valid cross-domain network targets with a network-qualified cross-domain resource, then typically if you ever got an alias search in there, your tables could assume that the alias resource is always going to be found somewhere inside your network. And you could limit the default table, which is used for alias searching, to only search the VTAMs in your own network, either in your subarea network or in your APPN network. That typically works best for most customers because they only have to predefine the resources that are cross-network, and maintaining adjacent SSCP and adjacent cluster tables for their own network is usually fairly easy to do also. Now, the question really is where should predefined C cross-domain resources be activated? Right? In subarea, you would probably only do it like you did on the previous chart with the gateway SSCP or with the alias translation. You would probably only predefine these cross-domain resources on CMCs and or gateway SSCPs. In APPN, it kind of depends on what level of ZOS communication server you're running. Now, in ZOS V1R4, we added a function called network qualified name mode for directory services database entries. This allowed you to predefine cross-domain resources on the subarea side of VTAM, and when you activate them, it would preload the directory services database with the information also. And once you've preloaded the information to the directory services database, directory services remembers that this is the one and only resource that can be found using an alias name search. And by doing that, directory services now has the ability, when an alias search request to come in, the APPN side can look up this entry in the database, determine that it is an alias to real mapping of sorts, and effectively convert the alias search to a real search before any search steps are actually performed by this node. Now, in order to be able to preload the directory services database with this information, you have to code two operands on the CDRSC, or at least have them default via start option. The first one is NQN mode equals name, which basically means I'm predefining it by name and net ID, but this is the only resource that should be findable by this name, by just the 8-character name. You also need to code the CP name operand on the CDRC definition. The CP name operand has always been allowed and has always been the trigger to predefine this information in the directory services database. By predefining these two operands on there, it causes us to load a special entry into the directory services database, specifically the entry that allows directory services to translate from an alias to a real name by fully qualifying the LU name. So now I'm going to go through 3 more examples that look very similar to the alias translation examples that I did earlier. In particular, we talk about a pure subarea network and what happens when we predefine CDRCs on only the CMC, for example. In a pure subarea network, it was very common for customers to only predefine the CDRCs on the CMC. Again, if an alias search request came in from the data host, we would look up the cross-domain resource first. We would find it by his alias name, but know right away what his real net ID is, and all subsequent searching would be fully qualified. This would be done before driving the NetView alias translation or the SME translation functions also. So the predefined CDRC can actually save driving of one of those exit routines or translation routines. In this case, a pure subarea network, because every search request has to go through the CMCs, if the CDRCs are predefined on the CMC, then that should be enough to fully qualify the search before we do any cross-network searching. And our second example, again, we migrated our network from subarea to APPN. The data host is an end node, the CMC is now an interchange node. And in this case now, if you predefine a CDRC on the interchange node, it's going to be on the subarea side of the interchange node, just like the alias translation functions are. So if a search request comes in from the end node via APPN, then the APPN side of the interchange node sees the search first. And so all of the APPN searching could theoretically be done unqualified before he sends the search over to the subarea side and sees the predefined CDRC. Right? So the APPN side searching would not be optimized, but the subarea side would be optimized if the CDRCs were predefined only on the CMC. Now the good news is that with that new NQN mode for directory services database function, you can actually predefine the CDRCs on the CMC only, and if you make sure you code the NQN mode equals name and or CP name operands on there, then it will cause us to preload the directory services database also, and now when the search request comes in from the end node, the APPN side actually has the ability to translate it to a network qualified name, and the APPN side can do that before doing any APPN border node searching, which would require us to select an appropriate ADJCLUST table. So in general, this works exactly the same way as the alias translation function. The CDRCs are only known to the subarray side, but if you use the new function on the interchange node, or on the border node in this case, then you do at least have the ability now to avoid the inappropriate, the unoptimized APPN searching before we kick it over to the subarray side. Now, one question a lot of customers ask me is, what do I code on this CP name operand? Because a lot of the times I don't know what node that the application in a different network really resides on, and even if I do know, when the failure occurs over there, he's probably going to move it around. The answer is it doesn't matter what's on the CP name operand. You can code whatever CP name you want on there. It's just the indicator to preload the directory services database. If we don't recognize the name, we'll still drop into broadcast logic, but we'll do it with the network qualified real name. And that allows us to choose the right ADJSSCP and right adjacent cluster tables before we actually do the searching. So it does not matter what you code on the CP name. You could code CP name equals neta.yoda if you wanted to, and it would work just fine. The key there is that you have to code the CP name operand. So this is now my recommendations for the alias name translation. Whether you're doing it with a predefined CDRC or whether you're doing it with alias translation functions like the SNE or NetView, the bottom line is that you really want to convert the alias name to a real network qualified name, that's the target resource of course, as close to the originating LU as possible. If you translate the name to a real name as close to the OLU as possible, that gives more nodes the ability to search using the network qualified name, which means choosing network specific adjacent cluster and adjacent SSCP tables rather than using default tables, which may search further than we really want to. All right? Again, you do it on the CMC if it's possible for alias translation. And if necessary, you would have to predefine things, for example, on the OLU host also. There are some cases where you might have to do that, but if you're predefining CDRCs correctly, even in an APPN environment, you should be able to get away with only performing these functions on your network nodes, not necessarily on your end nodes or your data hosts. There was one APAR that was added in V1R7 that allows the directory services management exit, which is also an APPN side function, to be able to take an alias name search and return it with a special return code that says, yeah, that alias name now has been fully qualified. I put the real net ID on there for you. And so there's a way to get the DSME to do it, but this is fairly limited, requires you to code a DSME exit, and I'm really not sure that most customers are probably not going to want to go to the trouble of doing that. So, by converting the alias name to a real name as close to the OLU host as possible, we give ourselves maximum possibility to use network-specific tables, which optimizes the searches for every top possible resource. That's the end of the first topic that we're talking about. The second topic that I'm going to discuss is called Who is my network node server? In an APPN network, the way you optimize searching is by sending directed searches rather than broadcast searches. But if you remember about the APPN architecture, not every network node knows about every end node. Remote end nodes on the other side of the network, I wouldn't know about unless I actually started a session with them. So if I want to send a directed search to any possible node, it's not necessarily possible for me to send a directed search to every possible end node. But because the network topology database includes every network node in my network, I should be able to always send a directed search to the network node server of every target resource. And so knowing who your network node server is helps you to understand exactly the kinds of entries that you want to put in certain adjacent SSCP tables so that you can optimize even the very first search and try to avoid the broadcasting. So we'll go through a little bit of a discussion about what a network node server is or who the network node server is, and then we'll go through a few examples to try and let you guess what the answers are. So optimizing search performance means avoiding the broadcast searches. The directed searches are always set to the target LU's network node server, not necessarily to the end node itself. And if you predefine cross-domain resources with both the net server operand and the CP name operand, then you might actually be able to avoid even the very first broadcast search. I think coding the network node server operand probably is a little bit overkill because in most cases you're only going to broadcast once anyway. And if you're checkpointing and reloading your directory services database, you're probably not even broadcasting that very first time. So I think this is probably a little bit overkill. I would code the CP name though, along with NQN mode equals name, so that you can use the NQN mode for DSDB entries function. All right, so who is the network node server for any given resource? If a resource resides on a network node, then that network node becomes the network node server for that resource. It certainly stands to reason since that network node is clearly the closest network node to the resource. End nodes always use a network node as their network node server, obviously, and it's always considered a native network node. I point that out because end nodes do not really have to use the same net ID as their network node server. End nodes can have any net ID they want, and they can still get network node server functions from a network node. The end node can change its network node server at its discretion. If it decides that its preferred network node server is now active, it can drop CPC sessions to 1, start them to his preferred server. If he loses a link to his current network node server, he can pick a different network node server and start CPC sessions with him. So there are lots of different reasons why an end node might actually change network node servers also, right? But remember that note about the end nodes being able to have a network node server with a different net ID. If an end node is in net B and his network node server is in net A, the end node is actually considered, the net B end node that is actually considered native to the net A network because his network node server is in net A. The question you have to ask yourself is, where do you send your directed search? You send it to his network node server, which is a net A network node server. So even though you're trying to reach a net B resource, you have to send it to a net A network node server. The net B end node becomes part of the net A native network, if you will. Now, if you have subarea nodes attaching to an APPN network through an interchange node, the subarea node acts like the end node, and the interchange node that he attaches through acts as the network node server for all of the resources that you can find in the subarea network. The reason we do that is because when we invented the APPN architecture for the interchange node function, we had to make sure that we could represent subarea attached resources in a way that APPN attached nodes, including non-VTAM APPN products, would understand. Since the upper bullet here with end nodes indicates that end nodes can have a different net ID than their network node server, that was a perfect model to build our interchange node function on, because oftentimes the subarea connection we're talking about is an SNI connection, and so the resources that are attached there are in a different net ID. But because end nodes can have a different net ID than their network node server, it allows these SNI attached subarea nodes to attach to an interchange node in my network and still look like their end nodes attached to a network node in my network. Still look sort of like their native resources from an APPN perspective. A lot of customers think that when we attach a subarea node, an SNI connection to an APPN network, that it looks more like a border node, an APPN border node type boundary, rather than an end node type boundary. And that is probably the biggest issue that customers have in defining their own adjacent cluster tables, is they always try to treat that subarea attached node as a border node boundary instead of as an end node boundary off of the network node or interchange node that attaches it. You'll see why that comes into play later when we talk about the adjacent cluster tables. It also means that subarea nodes could actually appear to have multiple network node servers, because there could be 2 or more interchange nodes that provide connectivity to the same subarea attached node. We'll see that one in the next chart also. So the bottom line is, the network node server for a resource, for an LU, is always the closest visible network node to that LU. And by that I mean, by closest visible, I mean sometimes you're going to cross boundaries where you lose visibility, but you'll always at least be able to see one hop across that boundary, and so that guy could potentially become the network node server. So the target LU's network node server is always the closest visible network node to the target LU's owning control point. So now I've got some examples that you can try out. The question on this chart is, who is the network node server for resources that reside on A3, which is this border node over here? Since the border node is always a network node, and since network nodes are always their own network node server, A3 is the network node server for all the resources on A3. Who is the network node server for A7, which happens to be an end node in this network? Since the only link shown is to A2, that's the only network node he's attached to, we have to assume that A7's network node. Okay, who is the network node server for this casually connected end node? An end node in net Z that attaches only to a network node in net A. And the answer for that one is it has to be that network node. So this is a case where a net A.A4 network node is the network node server for a net Z.Z9 end node. Again, even though the resources on Z9 are in net Z, they are considered native to the net A network because his network node server is a net A border node or network node. All right, who is the network node server for this subarea attached resource up here called Y8 in net Y? That's an SNI connection that attaches to the interchange node or border node called A1. Since the only connection we've shown is a subarea connection from him to A1, we have to assume that A1 is the interchange node providing connectivity to the subarea network, and so A1 would be the network node server for Y8. Who is the network node server for this guy over here in A5? I've got net IDs wrong here. This should be net y.y8, and this should be net a.a5. So just in case you're looking, those net IDs probably should be reversed. Anyway, so who is the network node server for A7, for A5 right here? You can see this subarea node actually has attachments to both A1 and A2. And so in this case, either A1 or A2 could act as the network node server for any of the resources that are on A5. And in fact, if A3 sends a search through A1 to get to A5, and A4 sends a search through A2 to get to A5, then it's possible that A3 thinks that A1 is the network node server for those resources, and A4 thinks that A2 is the network node server for those resources. That's not uncommon. It can happen even for pure end nodes. If an end node changes servers, there could still be some other network nodes out there that still think the old network node server is still the NNS. So this is not a problem. It's possible that more than one node thinks that different interchange nodes are the network node server for sub-attached resources at the same time in the network. So in this case, the A5 network node server could either be A1 or A2. That was a single net ID, if you will, with SNI connections. Let's try to make the picture just a little bit more complicated, and we'll talk about who we think the network node servers are in this picture. In all of these pictures, I'm going to ask you, who do we think is the network node server for C1? The node over here on the side. The first question is who does C2 think is the network node server for C1? And since we're in the same network and we can see everything, C2 knows that C1 is a network node, and so he knows that C1 has got to be the network node server for everything on C1. Who does A1 think is the network node server for C1? Well, the best path to get there is by having A1 go directly to C2 and not to C1. But A1 can't see into the C network. It can only see as far as that adjacent node. So in this case, the closest visible network node from A1's perspective to C1 is C2. So from A1's perspective, C2 is probably the network node server for C1. But it's also possible that the link from A1 to C2 goes down. And if that's the case, A1 could actually send a search down to A2 and then over to C2 and back up again. And if this is the case, A1 would see A2 as the network node server for the resources on netc.c1. So the answer for this one is that either C2 or A2 could be the network node server for the resources on C1 from A1's perspective. Who does A2 think is the network node server for the resources on C1? Well, if you are following the last discussion, then you're probably going to see that this is just the opposite. Clearly, A2 would go to C2 as the first route, but if that link was down, A2 would want to go up to A1 and then come back down to C2. So from A2's perspective, either C2 or A1 could be the network node server for C1. How about A4, the node way over here on this side of the network? Well, A4 could either go through A1 or through A2 to get to C2. So from A4's perspective, either A1 or A2 could be the network node server for C1, for the resources on C1. How about B1? This node way over here at the top right. If B1 is searching for a resource on C1, the reply coming back would indicate that, for example, if the reply came back through A3, it would look like A3 was the network node server for all the resources on C1, from B1's perspective. But B1 could have sent the search down to A4 instead, and if that's the way the reply came back, then B1 would see A4 as the network node server for all the resources on C1. Finally, if both of these links into B1 were down, B1 may have to send things down to B2 and have B2 send them across the wall. So from B1's perspective there, it would look like B2 was the network node server for all the resources on C1. So the answer to this one is that either A3 or A4 or B2 could look like the network node server for B1, from B1's perspective. The reason I bring all these up is because when you identify the nodes that could become the network node server in a board node environment, those are typically exactly the same nodes that you would want to put in an adjacent cluster table when you're searching for resources with that net ID. And so we're going to see later that an adjacent cluster table for net C, coded on B1, would probably have the A3, A4, and B2 entries in them. And finally, B2. If B2 was going to do a search for C1, then B2 could go to A4 and see A4 as the network node server. If that link happens to be down, B2 would go up to B1 and come across one of the other links. So from B2's perspective, either A4 or B1 could look like the network node server when we're looking for resources in netc.c1. That's the end of the topic on who is my network node server. I'm going to give a brief introduction now to subarea and APPN searching before we jump into tuning a subarea network search control or turning the APPN network search controls. In case you haven't noticed yet from my discussion so far, VTAM actually has two very distinct searching algorithms. They have the subarea searching algorithm and they have the APPN searching algorithm. Understanding either one of these algorithms can actually be a fairly mind-boggling task. But if you're trying to understand both of them, it gets a little bit more complicated. And if you're trying to understand how they interact, it is almost impossible. It's almost a career. And certainly I've spent much of the last 22 years doing exactly that, trying to understand the interactions between APP and subarea searching. Which searching algorithm do we typically use then when a search request comes in? The answer is we use the search request. Which algorithm we use depends on where the search came from. If the search starts on this interchange node, for example, then the subarea side is in control first because all resources in the network actually are owned by the subarea side of VTAM. If the search request, and that means the subarea search control, the subarea side gets control of the search first. If a search request came in from the subarea network, the subarea side search controls obviously get control first as well. But if the search request comes into this node from the APPN side, like from a served end node or across an APPN network boundary, a border node boundary, then the APPN side search controls are in control first. And the searching algorithm is in control first. All right? Now each of those two algorithms, subarea and APPN, have a way to pass the search request over to the other side so that the other side can do searching. In a subarea network that's done with ADJSSCP tables, as you'll see, in the APPN network you'll see that the subarea side is actually searched as part of an extension of a network node's end node search, if you will. Now, if you want to tune these things for performance, it's going to take a little bit of work, especially if you've got both APPN and subarea paths between the same two VTAMs. If you don't care which path is being used, then you can pretty much let it go, and everything will probably work fairly well. If you really want to make sure that one path is used over the other, for example, if you want to make sure APPN paths are used whenever possible so that you get the benefits of high-performance routing, then you need to make sure that you've got things set up to skew your searching toward the subarea. Now, there's a trade-off between how much searching you want done dynamically and how much you're willing to predefine to optimize the searching. There's usually a fairly straightforward trade-off there. The less you predefine, the less optimal your searching will be. The more you predefine, the less dynamics you use, the more you predefine, the more optimized your searching will be. And of course, the last bullet here says that complexity of this is significantly reduced once you migrate to a pure APPN network. However, as long as there's SNI customers out there, I think that's going to be fairly difficult for a lot of customers. The subarea searching works in a trial and error fashion. We basically use adjacent SSCP tables to build a list of adjacent VTAMs that we want to search. And then we basically search them one at a time, and if we send a search to one guy and it fails, we'll send it to the next guy on the list, and if it fails, we send it to the third guy. We do that until we hit the bottom of the list or until we find the resource. When we build the list of CDRMs that we're going to search, we do that using adjacent SSCP tables as well as a certain amount of SSCP dynamics if you allow them. Right? The tables that you define can be NetID specific. If you know he's in NetA, use this table, for example. Or CDRM specific. If you know he's owned by CDRM1, use this table. You can also code one that's NetID and CDRM specific. If you know he's in NetA and he's owned by CDRM1, I want you to use this table. So you have three different kinds of tables. And of course, you can also define a no NetID, no CDRM table, which is basically the default table. And we use it whenever we have an alias search. And we also use it whenever we have a search for a target NetID for which we do not have a NetID specific table or owning CDRM specific table, or both, NetID and owning CDRM specific table. If we can't find a better matching table, then we'll use the default table for any other searches that we have to perform. There is also a pseudo adjacent SSCP table called an ADJList, which is basically a cross-domain and resource-specific search list. I'll talk about that in a later chart when we have more time. The session management exit has an adjacent SSCP selection function which allows your exit routine to use whatever logic it wants to reorder and delete entries out of an adjacent SSCP table after we've built it, but before we've done any searching. So if you want, you can actually write exit logic that will reorder adjacent SSCP tables to optimize your searching even further. To me, most of the time that seems to be like it's a little bit overkill. Now the way we enhance subarea searching to handle the APPN search is that, I said in the adjacent SSCP tables, there's a special entry called the IST APN CP entry. And when we find that entry in an adjacent SSCP table, that's VTAM's indication to send the search over to the APPN side of the node and let the APPN searching do their thing, right? So sometimes you have to code the IST APN CP entry yourself. Sometimes you don't have to code the IST APN entry yourself because VTAM will add it automatically to the table under many conditions. So adjacent SSCP tables may or may not require changes depending on what your search order you choose, which we will talk about again later. But in general, that's the way we have the subarea side control when he passes the search request over to the APPN side. This chart here is an overview, a very quick overview of the APPN searching algorithms. The first step in APPN searching is not even a search. It happens when an end node attaches to a network node server and starts CP/CP sessions. The first thing he can do is register all the resources that reside on him to his network node server. And he can also indicate to the network node, that's everybody I have. If you're searching for anybody else, don't even bother me, right? Because if he doesn't reside here, I'll keep you informed of everybody else. If you have central directory servers in the network, you can also get the network nodes to register resources all the way up to the central directory server, right? In an APPN network, if we're searching for a resource, there are two different kinds. We talked about a directed search and a broadcast search. The directed search is targeted to one specific node, which may be adjacent or may not be adjacent. It could be across the network from here, right? A broadcast search is sent to everybody who's adjacent to me, and they in turn broadcast it to everybody who's adjacent to them, and eventually a broadcast search permeates the entire APPN network until all the network nodes get control. At that point, they can all search their end nodes and decide whether or not the resource actually resides on them or not. So broadcast searching can either be a network broadcast or it can be a domain broadcast, which means a broadcast search of all end nodes who want to be searched at the same time. In that case, we actually send the search to multiple nodes at the same time, and before we actually collapse the search completely, all of those nodes have to send us replies back. A central directory server can be used to reduce the frequency of broadcast searching also if you do have to broadcast. Without a central directory server, it's possible that every different network node in the network would have to broadcast for the same target resource name at least once before they cached it in their database. A central directory server is a way of making sure all of those broadcast searches are performed by one or two nodes in the network, and they basically compile a huge directory database of everybody that resides in the network. And any network node that's not sure where a resource resides would query the central directory server first rather than doing a broadcast search. The central directory server will respond from its database, or if it doesn't know where it is, it will perform the broadcast search on behalf of the other network node. Of course, we also have the adjacent subnetwork search, which basically uses adjacent cluster tables. This is sort of like the adjacent SSCP search, but it's really only used when you're searching across subnetwork boundaries. I shouldn't say that. Border nodes use these tables all the time when the target resource is across a subnetwork boundary or not. It's really only used if a node is a border node, and it's only used when we're in the broadcast phase, which means we're not sure where to send a directed search to. So the EBN searching is actually performed, if you will, as part of the broadcast searching. There's also a directory services management exit that gives you the ability to reorder, add, and remove entries from your adjacent cluster table in much the same way that you could add, remove entries from an adjacent SSCP, excuse me, not add. You could reorder or remove from an adjacent SSCP table. You can add, delete, or remove from an adjacent cluster table. Again, I'm not sure too many people are ever going to code a DSME. They're probably not going to go to the trouble. Instead, they would rather probably just code appropriate adjacent cluster tables and try to make sure all of their searching is network qualified. The next topic is on tuning the subarea network. I'm going to tell you what the subarea search controls are, and then we're going to walk through a sample subarea to APPN migration where we can actually use adjacent SSCP tables to, and show you how you would modify them during each step of the migration. So first of all, the subarea search controls. You've got the adjacent SSCP tables and maybe these ADJ lists that I was talking about. You've got dial retrial, dynamic adjacent SSCPs. This is your max SSCP, which is the depth that a search is allowed to go through. How many VTAMs can we send this thing? The S order, or the search order operator, is probably the biggest knob that you have, the most important knob to control. And then you've got some more dynamics down here on priority versus defined routing. Do we do things in defined search order, or do we remember which were successful and which didn't work, and use that to prioritize searches next time? I've highlighted the adjacent SSCP tables and the S order because those are basically the two that we're going to be talking about the most during this discussion of subarea search optimization. S order is the search order. It's the subarea search order, if you will. How do you want the subarea side to search the APPN network? Do you want the subarea side to search the APPN network first? Do you want the subarea side to search the APPN network last? Do you want the subarea side to search the APPN network sort of near the beginning? Or would you rather go in and code it in your table yourself? That's basically what these are all about. With S order equals APPN first, APPN and subarea, you do not have to code the IST APN CP entry in any of your adjacent SSCP tables. Instead, VTAM will automatically put the IST APN CP entry in each of the tables based on the S order. If you use S order equals APPN first, we will always make sure that the IST APN CP entry is added at the very top of the adjacent SSCP table that we use for searching. If you code S order equals APPN as opposed to APPN first, then we would tend to put the IST APN CP entry toward the top of the adjacent SSCP table, but there are a couple of other entries that could float above it in the table, like the predefined owning CDRM name, if you have that coded on a CD or a C. Or if you had already searched through subarea and found him through subarea, the learned owning CDRM name may be stuck in there. You'll see that on my next iBuster chart, but the bottom line is S order equals APPN prefers APPN, but does not always search APPN first. S order equals APPN first always, always, always searches APPN first. S order equals subarea, on the other hand, you might think that it means I only want to search the subarea network, but what it really means is I want to search the subarea network first. So with the S order equals subarea value specified, VTAM would tend to place the IST APN. That way we search all the subarea CDRMs first, and if all of those fail, we hit the bottom entry and we search the APPN network. S order equals adjacent SSCP was invented back when we first did this because we want to give you the ability to be able to search APPN first for some net IDs and subarea first for other net IDs. If you have some net IDs that are still SNI attached to you, then you really want to prefer subarea searching for those guys. On the other hand, for your net ID, if you're migrated to APPN, or for any border node connected customers who are APPN attached to you, for those net IDs you would want to search the APPN network first. So prior to, when we first shipped this support, there was no way to change the S order value on an adjacent SSCP table basis. It was one S order for the whole node. And so we gave you an S order value equals adjacent SSCP. And basically when you code this value, VTAM will not automatically add the IST APN CP entry to your adjacent SSCP tables. Instead, we rely on you coding the IST APN CP entry in the appropriate location in each table. You could code the IST APN CP entry at the top of the table for the guys that you want to prefer APPN searching. You could code IST APN CP entry at the bottom, for example, of the NetZ table to say that I want to try subarea first, but if that doesn't work, we'll try APPN last to get over there. You could also code it in the middle. I want you to search a couple of CDRMs first, and if that doesn't work, I want you to search the APPN network, and if that doesn't work, come back to the subarea side and we'll search a couple of more subarea attached guys. So that would work also. But more importantly, this guy allows you to not code the adjacent SSCP, the IST APN CP entry in an adjacent SSCP table. And with S order equals ADJSSCP, and no IST APN CP entry explicitly coded in the table, it means for this table, whenever you pick this table, I don't want you to search APPN at all. So there were ways to turn that off. Okay, remember that S order equals subarea is not the same as S order equals ADJSSCP with no entry in the table, right? S order equals subarea, we'll search subarea first, but there will still be a final step down there where we'll search APPN if we get that far. This is an iBuster chart that gives you an idea of the order that VTAM will search for all four of the different S order values, but also for the subarea SSCP order equals priority versus defined routing. Priority routing, again, tries to remember which paths were successful and which paths have failed, and tries to reorder the successful ones at the top, the failed ones at the bottom, and the untried ones in the middle. So that's one of the reasons why you can actually get some of your previous successes and stuff to occur before an APPN network search in the S order equals APPN case. You also see that the learned and coded owners, as well as a directory database query, those can all be done before the APPN network search. In other words, with S order equals APPN, it was the full search of the APPN network was still step 5, not step 1. The reason we invented S order equals APPN first was because there were customers out there who wanted to use APPN whenever possible to force the use of HPR. And we weren't doing that very well with sorder equals APPN. So we gave them sorder equals APPN first, and now you'll notice the APPN entry always is at the very, very top of the table for that value. Again, this table here prefers subarea as you go to the right, it prefers APPN as you go to the left. There's a whole bunch of bullets down here about quirks that you can do. I'm not going to go into those bullets right now, I think there's probably a little bit too much there, but this is a pretty good eye-buster chart that gives you a feel for what order VTAM will search for the various S-order and SSCP ORD combinations. ADJList we talked about very quickly before, and we'll go into them a little bit more now. An ADJList is a way to define an explicit adjacent SSCP table and give it a name. And then on cross-domain resource definitions, you can code ADJList equals the ADJList name, and it means whenever I'm searching for this cross-domain resource, I'm going to use that adjacent SSCP table, that ADJList. The thing about ADJLists is that S-order has no effect on them, SSCP ORD, priority versus defined routing, has no effect on them, learned and coded earning CDRM names, directory database cached information, none of these things have any effect at all when we're searching using an ADJList. We search only the entries in the ADJList. We always search them in the predefined order, and when we get down to the bottom of the list, if we haven't found it, we're done. That's why we call it one of those, what you code in the ADJList is what you get. It's a what you see is what you get adjacent SSCP table. Customers tend to use these when a generic search strategy is adequate for most resources, but you got a couple of them that are problems, and for those problems, you define a very specific search list for just those guys, give it a name, predefine a CDRC with that ADJList name on them, and now whenever we search for those resources, we use a very, very particular list. So, the recommended search strategy right now, it used to be to code sorder equals ADJSSCP, but that's not really good anymore because we've given you now the ability to code the S-order operand on each and every adjacent SSCP table. You do not just have to use the start option value for S-order. In fact, if you ever run into a customer who is using S-order as the start option value, they probably have not tuned only as the start option value, that is, they haven't coded on their adjacent SSCP tables, then they probably haven't really given a lot of thought to how they want to tune their network right now, at least. So what it allows you to do, the S-order on adjacent SSCP tables, what it allows you to do is code a different S-order for each adjacent SSCP table that you define. You no longer have to use sorder equals ADJSSCP and put the IST APNCP entry at the top or the middle or at the bottom. Instead, on some guys you can code sorder equals APPN first, and whenever we pick that table we always go the APPN route. And on other tables you can use sorder equals subarea, where we prefer subarea but we'll try APPN last. And on still other tables you can use sorder equals adjacent SSCP and not code the IST APNCP entry in it, so you basically get only search subarea type of table. You can code it on the network statement or on the CDRM statement. The network and CDRM statements effectively are the statements that start a new adjacent SSCP table in an adjacent SSCP deck. If you code it on the network statement, it will sift down to all the subordinate CDRM statements. If you want a lower level table to actually use the start option value, you can code sorder equals start op, which means whenever you pick this table, I want you to use the current start option value for the sorder. Notice, by the way, that if you issue the modify VTAM ops command to change the sorder value, it has an immediate effect on any adjacent SSCP tables coded with sorder equals start op. And the reason for that is when we activate the table, we do not remember the start option value in effect at the time we activate the table. Instead, we remember the fact that he wants us to use the current value. And every time we select that table for searching, we'll look at what the current value of the VTAM start option sorder is, and we'll use that value for that search. Remember that S-order is not allowed on ADJLists. ADJLists are always what you see is what you get. But if you want to mimic the same function like APPN first in an ADJList, all you have to do is code the IST APNCP entry at the top. Since we're not doing any dynamics or reordering, then that would always basically effectively work like an S-order equals APPN first ADJList. Alright, so the last topic under subarea tuning is the adjacent SSCP tables for a sample subarea to APPN migration. I show basically a network here where we're in net A and we're defining adjacent SSCP tables for the CMC and the backup CMC. Right now our CMCs have SNI connections to net C and to net B, but the whole network right now here is all subarea. So over here on the left I've showed you what a sample adjacent SSCP set of adjacent SSCP tables might look like for the CMCs in network A, CMC and backup CMC. The default table Basically says search the 2 CMCs first. If that doesn't work, search the 3 data hosts in my network. That's always a good practice. You might as well bug your own host before you start sending searches that may not really belong to other hosts, and in particular other net IDs. But if you can't find it on either the CMCs or on the 3 data hosts, then send it to these gateway hosts to see if the resource happens to reside there. Remember, this is the default table, so we would use this if we had an alias search and we weren't sure what the net ID of the target resource was. Here's my network A adjacent SSCP table. So if I know the resource resides in network A, then the only people I should search are the CDRMs that are in network A. And that's why you see just the CMCs and the data hosts in this table. Then I've got a network B table here, where I've got only my, if I know he's in network B, the only thing I should be searching are the 2 gateway hosts down here in network B. And I've got a network C table here that says whenever I'm looking for something in network C, the only thing that I should be searching is the guy down there in network, in the gateway SSCP in network C. So what we're going to do now is start by migrating part of our net A network from subarea to APPN. The data hosts typically become end nodes, the CMCs typically become network nodes, but an end node really isn't very useful without a network node server. So we pretty much have to migrate these 2 guys to network nodes or interchange nodes first. At the same time, I'm going to migrate one of my data hosts to be a pure APPN end node at the same time. So now, most of the net A network is still via subarea. I can still find everything just about via subarea. We've still got subarea connectivity between these 2 CMCs because they would need it in order to be able to take over each other's NCPs. So there's still subarea connectivity. There's also subarea connectivity to 2 out of the 3 data hosts. So 4 out of 5 of my hosts can still be found via subarea. That tells me I should be skewing my searching toward the subarea network. All right? So what do I do? How do I do it to do that? On my default table, I code S order equals subarea, and that floats the APPN entry at the bottom. I do the same thing in the APPN network, prefer subarea searching. On my net B and my net C tables, I actually code S order equals adjacent SSCP, and I do not code an IST APN CP entry in them, which means at this stage in the migration, if I know I'm looking for a net C resource, I am not going to do any APPN searching, I'm only going to do subarea searching. Now, you might look like that this resources on this data host over here might be a long time in finding them, but it turns out because that's an end node and he registers resources, one of the first search steps we do is query our directory services database. So you'll find that in many cases we'll learn about those resources even before we do our trial and error searching anyway. So even though we're mostly subarea, even the searches for the resources on that end node are probably optimized fairly well the first time through. Again, if your network is mostly subarea but still has a little bit of APPN in it, this is a way to configure your table so that almost all the searching is still performed optimally. Now I'm going to migrate a second data host to APPN. So now I've got 2 end nodes. My 2 network nodes are APPN and subarea attached, so I can consider them APPN attached also. So now it looks like most of the resources in the net A network can be found via APPN. The only ones that can't are the resources on data host number 1. So how would I go from preferring subarea searching to preferring APPN searching? You'll notice all I did was change the S order value on my default and on my net A tables from S order equals subarea to S order equals APPN first. Now all the searching prefers APPN searching. Now that will slow down the searching for all the resources on this data host. But once you've done your APPN search and couldn't find it, and you've done your subarea search, you will actually learn the owning CDRM name of that resource, and you'll learn that he's on data host 1. The next time you search, rather than picking the default table or the net A table, you'll pick the net A CDRM 1 table, the data host 1 table down here. So I coded an extra net ID and CDRM name specific table to handle that one straggling data host who still has not been converted to APPN. So once we've searched him and found him and we've updated the owning CDRM name to be data host 1, we will pick this table instead, and lo and behold, we'll actually search directly to him also. So the first search for the resources on data host 1 may not be optimal, but all subsequent searches will be. This little mini data host 1 CDRM table is a throwaway table. You really won't need it once you're pure APPN, but if you really felt like the searches for the resources on data host 1 were taking too long, you could certainly add the data host 1 table and optimize the searches for that case as well. The next chart here now shows that we have migrated everything to APPN first, to APPN I mean. So now there's no reason to perform any subarea searching at all inside our node, although we're probably still going to do it just in case. Well, we still have these entries in the table, so we would still search them in case you had to back off of APPN for some reason. Notice that the tables look exactly identical, except now I've deleted that mini table. That mini table for data host 1 is no longer needed because you'll never really find anybody on data host 1. He'll always look like he's findable through the APPN network instead. Remember that in both of these cases, the NetB and the NetC tables are coded S-sort equals ADJSSCP with no IST APNCP entry explicitly coded, which means whenever you're searching for a NetB or a NetC resource, the only thing the CMCs will do is search the subarea network, and presumably only these CDRMs, and so you'll always search directly down into those networks for the NetB and the NetC cases also. Throughout the whole step, that's true. Throughout the whole migration, that's true. So now I've shown you pure subarea, pure APPN, and all the phases in between, and there are ways to optimize searches in your network and beyond for all phases of your migration from subarea to APPN. What happens now, for example, though, if we're a NetC guy here, just NetC adjacent customer, decides he wants to do APPN and use border node to you instead? What would you have to do in that case? Well, on the subarea side, the only thing you have to do is tell your subarea side searching algorithm for those net IDs, you want to be able to search APPN first. So in this case, if we migrated the NetC network to APPN and used border node instead, all you would do is change the S-order operand on the NetC table from S-order ADJSSCP to S-order APPN first, and now VTAM automatically searches the APPN network first for that net ID. Why would I keep the CDRM name in this table, even though I know VTAM is putting the IST APNCP entry in there first? If you found a problem with your migration to APPN and you had to back out, you could kill the CP/CP sessions, and if your SNI connection and CDRM sessions were still there, we would immediately start using them again as the backup path. So that's the reason why you might still want to keep your subarea CDRMs in here even after you've migrated to APPN. You may, if the CDRM sessions and the links are still there, you may want to use them as a backup path in case something is wrong with your APPN path. We'll go into the SNI to EBN migration quite a bit more later, especially on the EBN searching. In fact, we're going to do it as part of this topic right here, which is tuning the APPN border node searching. Remember that in APPN, most of the search steps, like broadcasting your domain and broadcasting the network and using central directory servers, most of that is pretty much architected, and products have to do it according to the architecture. But when you get to border node searching, it's not really clear that any APPN network node knows what boundaries to search across first when you're looking for any given net ID. So when you're doing APPN border node searching, you really do need to spoon feed VTAM with the correct ADJSSCP tables, or allow a certain amount of dynamics to occur possibly. So we'll start first with an introduction to APPN border nodes. In particular, what I want to do is introduce the chart that I'm going to use for a lot of my further discussion. I've got a fairly complicated chart here with a NetA APPN network in the middle, a NetC on the left, and a NetB APPN network on the right. And in addition, all of these other net IDs like NetY, NetZ, NetV, NetU, all of these guys are SNI connections attached to one or more of the interchange nodes in these networks. All right? And for the purpose of this discussion and most of the rest of the discussion, I assume that you can use any path shown on this diagram to get to any net ID shown on this diagram. In other words, if I'm in NetC and I'm trying to get to NetV, but I can't get there through A1, I'm allowed to actually go through A into B and then come down again. I'm assuming that all the paths that are shown here are valid. It's not like I'm sending garbage through another customer's network that I shouldn't be using. So let's talk a little bit about some terminology first. Entry border node is the term that we give to a border node who receives a search request across the network boundary, because that's the entry point into that network. So for example, if a search started in network C and C2 sent it over to A1, A1 would be considered the entry border node for that search. At the same time, an exit border node is the border node that sends a search request across a network boundary into another network. So for that same example, where a search originated in NetC and C2 sent the request over to A1, C2 would be the exit border node in the NetC network, and A1 would be the entry border node in the A1 network. If that same search then flows through A3 out to B1, then A3 becomes the exit border node in the NetA network, and B1 becomes the entry border node in the NetB network. Now, entry and exit border nodes are not distinct roles. It's possible that the same node is acting as both the entry border node and the exit border node. For example, if C2 sent a search request into A1, and A1 had a border node, a direct connection over here to B1, and sent the search that way, then now A1 becomes the entry border node as well as the exit border node for that search in that example. All right, so the entry and exit border nodes may be the same nodes, they may be different nodes, and certainly there's an entry and an exit border node in every intermediate network, right? If you're going to come in and leave, then somebody's got to enter and somebody's got to exit, so there's typically an entry and an exit border node in every intermediate network. Now the origin border node is a little bit confusing. It's the name that we give to the first border node in the originating LU's network to get control of the search. He may not be the entry border node. Well, he certainly wouldn't be the entry border node because the OLU is in your network, so it couldn't have come in across the network boundary. He may not be the exit border node either because, for example, C2 might send it to C1 might send it to C2 to get across the network boundary. In that case, C1 would be considered the origin border node, C2 would be considered the exit border node. All right? It's also possible that if C2 is originating the search, he could be both the origin border node and the exit border node. And the last thing I want to talk about is peer border nodes. Peer border nodes are border nodes that are in the same APPN topology subnetwork as other border nodes. So C1 and C2 are peer border nodes. A1, A2, A3, and A4 are peer border nodes, and B1 and B2 are peer border nodes. The reason you need to understand peer border nodes is because, like in this example, A1 does not have connectivity to every possible adjacent network. He's only got connectivity to the net C network, APPN network is, through border nodes. If A1 wants to get to net B based on this diagram, he actually has to send the search to A3 or A4 to get into the net B network. In that case, A1 sends a peer border node search over to A3 or A4 to get it outside, to allow those peer border nodes to also search across any network boundaries that they have. That's the idea of a peer border node. All right, so let's talk about little known facts about border nodes. When a peer border node search is performed, for example, when A1 sends a search request to A3, asking A3 to look across network boundaries, the only thing that the receiving EBN is allowed to do is search the non-native networks that's attached to him. All right? It allows that receiving EBN to search as adjacent networks. The receiving end node, EBN, is not allowed to reroute that peer border node search to other peer border nodes in the same network. Instead, if A1 sent to A3 and A3 couldn't do anything with it, he would reject the search and A1 would then try A4 and let A4 try. So it's the entry border node or the origin border node's responsibility to search all of the peer border nodes in his network. Okay? When is an EBN not an EBN? And what I mean by that is, when can you display in the topology database, show me all the border nodes, and not see somebody who's coded with border node equals yes? When you code border node equals yes, it means that you're defined as a border node. But if you don't have any active links across APPN network boundaries, then you really can't act like a border node. So why would you want people sending you border node searches when you really don't have any network boundaries to search across? So that's the reason why. Border nodes do not report themselves as border nodes to the topology database until their first inter-subnetwork link is activated. As soon as they do, they'll send out a topology update saying, I'm a border node now. And everyone will start searching them as peer border nodes. So when is an EBN not an EBN? When you define a border node with BN equals yes, you've configured him as a border node. But if he does not have any active links across APPN network boundaries, then he's really not capable of acting like a border node. Right? He can't be an entry border node, he can't be an exit border node. There are no network boundaries. So this is basically a case where a border node will not report himself to the topology database and to other nodes as being a border node unless he has an active inter-subnetwork link. He'll send out a topology database saying, I'm a border node now, you can send searches to me. And as soon as his last inter-subnetwork link goes down, then he'll basically send out a topology database update saying, I am no longer a border node. That's very important because it affects the way some SNI type searching may be performed. If I don't have any active inter-subnetwork links, then I will not receive peer border node searches from other nodes, and that might be the only way that you configured him to search that guy, which is not the right way to do it, which we'll show you later, but there are certainly possibilities. So remember that a border node is not a border node unless he has an inter-subnetwork link. At the same time, when does a border node search like he's a border node? When does he pull out those adjacent cluster tables and start using them? In this case, even if I'm the origin border node and I do not have any active inter-subnetwork links, if I don't know where the resource is, I am still going to pull out my adjacent cluster tables, and I'm still going to use those to do my searching. So I always use adjacent cluster tables for border node searching, but I may not be able to search all the peer border nodes in my network because some of them may not have told me they're peer border nodes yet if they don't have any active inter-subnetwork links. Hopefully this will come clear when we talk about some more of this in a little while also. So the next chart we're going to talk about are APPN search controls. There are some, more than you might think actually. We've got the adjacent cluster tables, which basically define how border nodes do their searching. I've already talked to you about Alias search and auth nets, which you can code on adjacent CPs that represent non-native nodes. to prevent alias searches from coming in, and also to prevent only the network qualified searches that you think are authorized to come in. But you've also got this border node dynamics equals limited, full, or none, and that probably is the primary control that you have other than the adjacent cluster list. You also have subnet visit count, which is kind of like SSCP visit count. We'll go into that a little bit also. There are a few others here that you might want to look into, but in general, those are the biggies. The bold ones are the biggies. Let's talk about border node dynamics first. This is the one that we thought would be the saving grace for all EBN searching. Border node dynamics equals full means I want this border node to always search every possible place that he knows about when you're searching for a resource. Do all possible searching. Look in your topology database for any border nodes, look for any adjacent non-native border nodes, basically search everything that you possibly know about. Border node dynamics equals none means I don't want you to do any dynamic searching at all. I want you to look for adjacent cluster tables, and if you find one that works, then I want you to search only the entries that I put in there. I don't want you to put any dynamic entries in there. You may or may not want to reorder them depending on being ORed, but the bottom line is we would not dynamically add any entries to that list. You have to predefine everything. BN equals limited means we want to do intelligent searching. What that means from your perspective would be, if I'm looking for a net A resource, then I'm going to search every border node that I know about who has a net A network qualification. If I'm looking for a net B resource, I'm only going to search the net B border nodes. So that way, if we're looking for a net B resource, it makes sense that we should only search through the guys that have the same net ID of the target LU name. Unfortunately, that does not really hit all of the different cases. Sometimes you still have to code adjacent cluster tables for some weird conditions. One of the weird conditions is, for example, if, for example, in net A, sometimes you've got net T resources. If I've got casually connected end nodes that are net T or net Z and they're attached to my network and I'm their network node server, or if I use the non-native network attach function, or if I've got LEN connections that have different net IDs, or if I've got SNI connections that have different net IDs. In all of those cases, you want to be able to search the native network, which is net A, even though the target net ID you're looking for is not net A, right? With intelligent searching, we would only search the net A network, or the net T, or if you're looking for a net Z resource, we would only search the net Z border nodes. And if the net Z happens to be an end node, you don't have any net Z border nodes, you only have a net Z end node. So the idea here is even with BN equals limited, the intelligent version of it, there are many cases where you're going to have to predefine some extra entries in your adjacent cluster tables anyway. The second case that's obvious is if you're going through intermediate subnetworks. You have to go from net C through net A to get to net B. If you're looking for a net B resource and you're in net C, there are no adjacent border nodes that are in net B. So you're not going to find the target resource using limited searching, border node dyne equals limited, unless you tell him you got to go through net A to get to net B and put the net A border nodes in the net B adjacent cluster table. All right, we'll talk about this a little bit more also. Finally, we always allow the border node dynamics option and the BN ORed option starting with V1R9 to be coded on each adjacent cluster table independently. So that's just a little enhancement that you can use to try to tune your searching a little bit more. So we're going to talk a little bit more about how BN equals full, none, and limited work, and then we'll talk about what this recommended search strategy will be afterwards. But first, let's talk about the subnet visit count start option. This is how deep should the search go. The subnet visit count does not count how many network boundaries you cross. It counts how many networks are involved. And my network, the originating LU's network, has to count as one of them. So a subnet visit count of 3, which happens to be the default value, basically means that net C can send it across to net A, and net A can send it across to net B, but it can't go any further. That's 3 subnetworks, C, A, and B, right? 2 boundary crossings, but 3 subnetworks. So if you think you need to go from C through A to B, and then across another border node connection to D, you may actually have to jack up the subnet visit count to 4 on some adjacent cluster tables, or maybe as the start option value, depends on how you want to do it. You can code it either as the start option, or you can code it inside the adjacent cluster tables on the network statement, or even on the net CP statement. So this is an example of an adjacent cluster table. You code the ADJCLUST V build, type equals ADJCLUST. You put your network ID on here, which basically we're going to make this one the default table, so it's border node dynamics equals none is what I'm going to use right here. And then I basically list a bunch of adjacent cluster guys. I call the entries here, their CP names are over here basically, but you can refer to them by entries. So this gives you an example of the kinds of nodes that you're allowed to put in an adjacent cluster table. The first entry, and by the way, we're coding this sample adjacent cluster table for the node net-a.a4 in that big picture that I was showing, which was the upper right corner of the net-a network, excuse me, the lower right corner of the net-a network. right? So what nodes can you put inside the adjacent cluster table? The first one you see inside here is my name. In other words, A4's name is in the net A or the default table. Why would you ever want to code your own border node name inside the table? Finding my own name in the network, in the table, basically causes this border node to initiate a search of the native network. That means the broadcast search, the central directory server search, the interchange node search, the subarray searching, and the end node searching, all of that kind of stuff. Right? Includes the end nodes, the ISANs, and everything SNI, regardless of the net ID. So why would you want to put your own name in there? Why doesn't VTAM always automatically search the native network? Well, consider what would happen in the previous diagram if network C sent a search request for net Z into net A. Probably a bad example. Let's say net C was sending a search for net Q into net A. Do I want to broadcast every node in the net A network when I'm looking for a net Q resource? Probably not. What I would rather do is send the search request only to where I think the net Q resources will reside. On the other hand, if a request comes into that network from net T, and I happen to have a casually connected end node called net T in my network, well, in that case, I do want to broadcast my own network, because that's the only way I'll find all the end nodes that are served in my network, is to kick off a native broadcast, right? So the idea here is that by coding or not coding your name in the table for every target net ID, you now have control over whether the native network is searched or whether we simply skip into peer border node or adjacent non-native border node searching. So that's what the special incantation is for putting your own name in the table. It basically means that's when I search the native network. And you can either put it at the top of the table, middle of the table, or bottom of the table, wherever you like. The other possibilities for names that you can code in an adjacent cluster table are border nodes who are in different networks, but they're immediately adjacent to you. Adjacent non-native border nodes. In A4's case, he had links to both B1 and B2. So clearly I would want to put those in a table if I was creating a table that would allow me to search everywhere. And the last thing that I can put in the table are all the peer border nodes. A1, A2, and A3 are A4's peer border nodes. So those are the types of entries you can put in the table. You can put your own name in the table, you can put any peer border node in the table regardless of whether he's adjacent to you or not, because we can tell where they are from the native topology database, or any non-native adjacent node that's not an end node, basically, or like a border node or a network node or something like that. Those are the other cases. They have to be adjacent to you, but if they're non-native, you can put those names inside the adjacent cluster table also. All right, so now we talk about subnetwork routing lists. What exactly is a subnetwork routing list? Well, we only have one table for each net ID. And if we code that table, if we pick that table and move our pointer through that table as we're searching, what happens if I've got 5 searches for the same net ID going on at once? One guy's moving the pointer around might screw up everybody else's. So instead of using the adjacent cluster table itself to do our searching, what we do is we use the adjacent cluster table, the entries from the adjacent cluster table, along with any dynamically allowed to be added entries based on BN dynamics, and we use the two of those together to create a subnetwork routing list. We use the subnetwork routing list for that search, for one search, and when that search is done and we get to the bottom, we throw that table away. If there are 5 searches going on, each one of them come in, each one of them grab the appropriate cluster table, each one of them figure out what dynamic entries are allowed, they come up with a subnetwork routing list. So basically it's the cluster table augmented by dynamics and priority routing that we actually use for the search request. Right? It's always composed of the cluster table entries plus any dynamic entries that might be allowed. How many dynamic entries might be allowed? Well, that kind of depends on your BN dyne value. So here's another little example. Assume that we have no adjacent cluster tables defined, and we're going to use the following subnetwork routing list on A4. This is what the subnetwork routing list would look like, depending on what you coded for BN dyne, either on the table or as the start option, depending on what we're using. For border node dynamics equals none, there's no adjacent cluster table, so there's no entries in there. We're not allowed to do any dynamics, and so we basically do no searching. This is very, very interesting because I know customers who have brought up a VTAM and they said, well, you know, he's not going to be a border node yet, but he's probably going to be a border node in the future, so I think I'll configure him as a border node right now, but to make sure we don't do any border node searching, I'll just code BN dyne equals none. And when you bring that guy up with BN equals yes and BN dyne equals none, what you find is that now you can't find anything that's APPN attached because we're not allowed to do any searching. So instead you code border node dynamics equals limited. With border node dynamic equals limited, there are no adjacent cluster table entries, but there are dynamic entries, and how many dynamic entries would depend on the net ID of the target resource. If it was net B, I'd probably have 2 entries to put in there. If it was net A, I'd probably have 3 entries to put in there. But if it was net C, I probably wouldn't have any entries to put in there, and that's because A4 does not have visibility to anybody in net C. Okay? So, with border node dynamics equals limited, the actual subnetwork routing list is composed of only the dynamic entries, and how many would depend on the actual net ID. On the other hand, with border node dynamics equals full, there are no predefined entries, but we're allowed to put any and all dynamic entries in there that are possible, and that would become our subnetwork routing list. And so again, A4 could actually put all the net A border nodes in there, plus the 2 net B border nodes in there, because A4 knows about everyone in his network, and he knows about all the non-native nodes that are adjacent to him. So let's try another little exercise. We've got border node dynamics equals limited right now, and we assume that we have no adjacent cluster tables defined, and we're defining subnetwork routing lists that would be used by A4. The question then is because what net ID are we looking for? If we're in A4 and we're looking for a net A resource, there are no predefined entries, there are 4 dynamic entries, all 4 of the net A border nodes, and so that would be our subnetwork routing list. What if we were looking for a net B resource? There are no predefined entries, there are 2 adjacent non-native border nodes with net B, and so they become my subnetwork routing list. Okay? What about net C? We're on A4, remember, and we have no visibility to net C. So in net C, no predefined entries, no adjacent non-native nodes that are in net C, so we don't do any searching. And that right there is a perfect example of why BN equals limited is not going to work very well in the configuration that I'm showing you. A3 and A4 will both have to, if they're searching for net C resources, they actually have to predefine names for A1 and A2 in order to get themselves over to the C network. The same is true for net T, which happens to be a casually connected end node in net A. If you don't code any entries in the net T table, then you're not going to do any searching. In this case, the net T table should probably have at least my border node's name in it, so it forces me to search the native network and find the casually connected end node. SNI attached guys are the same way. They look like casually connected end nodes, and so the same is true. I'm not going to find them unless you actually go in and code tables. And in this case, you would actually want to code a netx table with my name in it so that I do a native network search and therefore find everybody who's natively attached. Remember that subarea SNI attached guys look like they're casually connected end nodes, so they actually look like they're part of the native network. Finally, if the request coming in for the target resource does not have a fully qualified target name, we're searching with an alias search, then basically border node dynamics equals limited works like border node dynamics equals full when you're searching using an alias name. So again, it kind of looks like you put everybody in there that you know about as dynamic entries, all the net A border nodes and all the adjacent non-native border nodes, which happen to be the 2 in net B. Finally, I want to talk about a little bit more about prior search history. BN equals limited does not do just the border nodes that have the same net ID as the target LU name. There is one more caveat to that one, and that is if I receive a search request through a border node with some foreign net ID in it, I will remember that I can get to that foreign net ID through that border node and search backwards the next time I look for the foreign net ID. In this example, if a netx SNI attached resource came through a net B2 border node and into A4 with a search request, the request came from the netx LU, then the A4 border node will remember that he can get to netx resources through netb.b2. Notice he does not put netb.b1 in there. He does not assume that all the B networks can get to netx. He only assumes that the one that the search came in through can get there. If you got to search in through both of them, you put them both in here. But right now, we only add entries to that list, that dynamics list, if you will, for searches that actually come in through an adjacent border node. We'll put that border node's name in for the originating LU's net ID. And again, next time we search for netx resource, we will be allowed to go through B2 for that. But again, you have to learn this first, and you don't learn it unless you've got BN equals full turned on, for example, for a while. So in general, BN equals limited does not work very well in this case, unless all those intermediate node hops and some of the other ones, unless they're actually the ones starting the search first. Okay, so summary of the possible BN options now. Border node dynamics equals full, it works all of the time. If you're ever having a problem reaching somebody, flip this on and it should work all of the time. Notice that searching is not going to be optimized. It can result in a lot of unnecessary CPU in your network. It can also cause you to send searches into adjacent customer networks that shouldn't belong there, and so they may eventually call you up and say, what are you doing sending the search into my network? So in general it works great, but you cannot possibly optimize it. BN9 equals limited is the most intelligent searching option available, but it really only works for the simplest of APPN networks. No SNI, LEN, EndNode, or non-native network attached capability. You don't have to go through intermediate networks to get to the target resource, and you also don't have to go through peer border nodes to get to the target resource. I'm guessing that 99.99% of all customers will have at least one of these limitations in place, which will allow BN9 equals limited to not work. So at the very least, they will have to augment their tables with those extra entries. The bottom line is, if this doesn't work very well, and this rarely works very well, the only way that you're ever going to get your searching to perform well is if you're in this category right here. You use border node dynamics equals none, and then you predefine the adjacent cluster tables that you want to do for all the searching. I'm guessing that most customers will probably want to use BN9 equals none. And that's why the rest of this presentation on EBN search controls shows you examples of what adjacent cluster tables would look like for any given net ID from any node's perspective. So we'll go into that topic right now. I'm looking right now at net-a.a1, and we're coding adjacent cluster tables. We're going to code them with border node dynamics equals none. We're going to code them for every net ID that you see on this chart. All right, so let's start by saying, what would you want to put in A1's adjacent cluster table if you were looking for a net A resource? If I'm looking for a net A resource, it could be anywhere on any of these nodes. It could also be on network nodes in the middle who are not border nodes. The only way to find them all is to basically force a search of the native network, which means you want to put your own name inside the adjacent cluster table. So the net A network statement would basically have one cluster table, would have one entry in it, and that would be A1's name. On A1, that is. All right, what would we do? On A1, what kind of cluster table would we build if we were looking for a net T resource, which is this casually connected end node? Well, casually connected end nodes are found by doing a native network search. Even though the net ID is not net A, you have to do a broadcast of the net A network to find the net T resource. So the net T adjacent cluster table would also have just one entry in it, and it would be my name. Force a search of the native network. What about the net U network? That's an SNI connection off of A3 here that you can't get from anywhere else on this picture. The only way to get there is through an SNI connection off of A1. The tendency is to put A3's name in the adjacent cluster table on A1. The reason you can't do that is because A1 does not always see A3 as a border node. If A3's one and only inter-subnetwork link to B1 happens to go down, then A3 will tell everybody in his network, I'm not a border node anymore. And if A1 tries to search over to A3 to get to you by a cluster table entry, we're going to prune A3 out, say, oh, that guy's not a border node, I'm not supposed to search him yet. So you basically pull it back out again. So the searching to net U would work fine putting A3 in there as long as this link was up. If this link was down, it would not work. For that reason, I would never code A3's name inside the net U table. Instead, these SNI guys look like they're end nodes attached to us, kind of like this net T guy. If the only way to get there is through an SNI connection off of me, I have to force a search of the native network and let him search his served end nodes, including the subarea network, in order to find this resource. So the net U adjacent SSCP table, adjacent cluster table, also has just one entry in it, and it's my border node's name, A1. So once you find out that all three of these guys essentially have the same table, you can collapse them down together into a single table, or a single definition, that says for A, T, and U, I want just one entry in my table. All right? So the next one is, what happens if A1 is trying to get to a net C resource? Well, everybody understands that he'd probably want to go to C2 first, because that's a direct connection to the net C network. But if that link happens to be down, A1 would want to send it through A2 to get down there. And so now, in the cluster table entry, we want to provide not only the non-native border node's name, but also the peer border node who can also get me over to net C. So the net C adjacent cluster table would have two entries in it. Go to C2 first, and if that doesn't work, try A2. What about net Y? If you take a look closely at net Y, the only way to get there is through an SNI connection off of this guy. So getting to net Y is basically the same as getting to net C. I can go directly to C2. If that doesn't work, I can go through A2 to get to C2. So my net Y table basically looks exactly like my net C table. And when I find that out, I basically collapse those two together, and I call this one my through network C table. And basically for both, for net C and for net Y, those are the two entries that I want to search. All right, what would we do if we want to get to the net B network? Remember, we're at A1, and we're trying to get into the net B network. The only way that A1 can send requests over to the B network is by sending them through his peer border nodes. So he would put A3 and A4 in there. That is the net B net ID table. What about the net X table? The net X table is this SNI connection off of B1, and that's the only way to get to net X. All right, so if I were going to try to get to net X in this case, I would basically, from A1, the same thing is true. I have to go through my peer border nodes to get to net B just to get to net X. And so my net X table looks a lot like my net B table. And when I see those two are identical, I collapse those two together too and call it my through net B table, which has A3 and A4 in the list. Got a couple more to go here. Let's try our net V table. The net V table, I can find net V as an SNI connection off of A1. I can also find net V as an SNI connection off of B2. So if I'm allowed to use either of those two paths, I would typically code them in the order that I would prefer them to be searched. So one of them looks like an end node attached to me. So I would actually put my name in the list, A1, search the native network, find the SNI attached guys. That's one of them. If I wanted to find the alternate path because that didn't work, I would want to get down here into net B. So it would look like a net B table would get me down there, and from A1's perspective, the net B table looked like it was A3 and A4. I could either go this way or I could go this way to get over to net B, which gets me down to net V. So the net V table in this case becomes a 3-table entry. Search the native network first to see if there's a way. If that doesn't work, try going through A3 and A4 into the B network and down. All right, and finally, we have a net Z case. Net Z can be found either through here, or it can be found through net C. So what would the net V table look like? From A1's perspective, this one looks like it's probably closer, so I would probably try C2 first. I would try A2 second in case my direct link was down. If that didn't work, I would have to go through A3 and A4 to get over to here into net Z. So for a net Z table, it would look like C2, then A2, then A3, and then A4. That's the net Z table. Looks fairly complicated. Hopefully once you understand who network node servers can be and stuff like that, and hopefully once you understand that SNI connections should not be treated like border node connections, don't think you have to do peer border node searches to get to them. Instead, SNI connections should be treated like end node connections. Force a search of the native network by putting your own name in there for anything that's SNI attached to you. Now, the A2 network looks very similar. I'm going to show you all of these at once, except for one thing. If I'm trying to find things in the native network, instead of having A1 in there, I have A2 in there, because that's my border node's name. In fact, if you went through these tables, pretty much any time you saw A1's name, you would put A2's name, and any place you saw A2's name, you'd probably have to put A1's name. Right? That would be the difference between A2 and A1. Now, some people have made it interesting point to me, and they basically tell me, you know, if these tables between A2 and A1 are so similar, why can't I create just one set of adjacent cluster tables and put them in a table that I can share between A1 and A2? Because A1 and A2 at least have symmetry. They have the same connections, if you will, over to the adjacent network over here. There's a very good reason not to share adjacent cluster tables in an APPN network. Notice now if A1 is trying to get to C, the path is C2 versus A2. And if A2 is trying to get to net C, it's C2 and A1. So if you were going to create a consolidated table for both of them to share, it would have to have a C2 and A1 and A2 in it. It would have to have all three of them in it. The problem is that when A1 searches with that table, he's going to find his own name in there second, and he's going to force a broadcast of the net A network, when all we're really trying to find are resources over here. When A1's searching, we shouldn't have to search this network. We should do that direct search, and we should do a peer search, but not search me. So I move A1 down at the bottom, so it's the last entry in my list. But now when A2 is using that table, he sees the A2 entry second. And the A2 entry forces him to do a network broadcast. So the bottom line really is that if you share tables, you usually end up putting too many entries in. The too many entries are usually my name, and they force a broadcast search of your network when it's really not necessary or even desired. So that's the reason why I tell customers, when you're defining adjacent cluster tables, do not share them. You really need to define adjacent cluster tables for every node from his perspective of the network and where the net IDs are. If you try to share things, you will not get optimal. If you don't share things, you'll find things go fairly straightforward. It's a little bit more definition, but searching will be much more optimized in that case. I'm going to skip over the net3 table. I'll go through just some of the net3 table just to make sure we understand what we're doing here. If A3 wants to search for net A or net T or net U, which can only be found through net A, he puts only his name in there. That looks right also. If A3 is trying to get over to net C or everything through net C, A3 has no connectivity over to this network, so he has to go through A1 or A2 to get there, and that's why you see this table. If I'm trying to get to net B over there, I have to find all the paths to get myself into the net B network. One of them is the direct path through B1, the alternate is through my peer border node A4. Now, once it got to A4, there are two different ways to go. That's not A3's problem, that's A4's problem. A4 has to take into account that there are two links over there to use. If we're trying to find net V, which again is findable through either net A or net B, then A3 would force a search of my own network, which would broadcast this and find served end nodes, including this one, which is SNI. If that didn't work, he'd go over to B1, and if that didn't work, he'd go down through A4 to get over into the B network where the other SNI link to net V is. So you get the idea. All of these things basically look very similar to the way A1 did it, but from their side of the network. And from A4's perspective, you'll notice, if A4 is trying to get to net B, A4 would try B1 first. If that didn't work, he would try B2 second. If that didn't try, he could go through his peer border node A3 and get over there also. So another example basically of how this would work. If you're trying to get to a net Z network from here, net Z can be found here. It can also be found all the way over here. If we were on A4 and we were trying to get to net Z, we've got a path this way through B1, a path this way through B2 and up, a path up through A3 and over for that one over there, but then I can also get through from over here, which means going through A1 and A2 also, and that's why you see this table. You see B1 and B2, then you see A3, my peer border node over to net B, and then you see my two peer border nodes that get me over to net C and then out to that net ID. So again, all of these entries are valid entries. I would probably use defined routing for all of these too, because really, we're coding the shortest path first. All right, we'll go through one net B table here, just for grins, okay? The net B table has a point that we want to make at the end of it, that's why. Okay, so now I'm on B1 over there, and we're trying to get to either net B or net X, which can only be found through net B. And so again, you only put your own name in the list, which is B1. That forces a search of this network. It finds casually connected end nodes as well as net B resources. It also finds things across SNI boundaries. So that will definitely find your net B and your net X resources. For your through net A, everything that you find through net A includes net A, net T, net C, net Y, which you can only find through net A, and net U, which you can only find through net A. So A, T, U, C, and Y are all net IDs that you can only find by going through net A. And how does B1 get to A? It goes through A3, or it goes through A4, or it goes through B2 to get to A4. Right? When I'm trying to find net V, one path is through net B, one path is through net A. So one of them is to just put my own name in the cluster table, forces a search of the native network, including SNI connections, and I find it. If that doesn't work, I'll try going through A3 to get to that SNI boundary. If that doesn't work, I'll try going through A4 to get to that SNI boundary. And if that doesn't work, I'll go through my peer border node to go over and get through that boundary. So all of those guys work also. They all look very similar. But before I move off this chart, let me ask you another question. Can you think at all, you got this through net A network right here, can you think of any reason at all why you might want to take that table and actually split up into a net C, AT and C in one, excuse me, AT and U in one, and net C and net Y in the other? Is there any reason why you might want to separate some of those tables? Why might you want to split the net A, T, and U table from the net C and Y table? Or why might you want to divide up the net V from the net Z table? The answer is, when you're trying to get to some of these guys, you need a subnet visit count of 3. But when you're trying to get to others, you only need a subnet visit count of 2. So if you wanted to prevent searches from going too deep, you can actually predefine these in a way where the subnet visit count makes a difference. So basically this gives you the idea. On NetV, you could actually code a NetV table that's separate, and you could basically say if I'm trying to get to NetV through these 3 guys, I want a subnet visit count of 2. Otherwise, I just want to do the broadcast of my own network. And the same is true for NetV. If I'm going through NetZ, if I'm going through NetZ through my own network, I don't care what the subnet visit count is because I'm only going to do a broadcast of my own network. But if I have to go through NetA to get there, then I want to give myself a subnet visit count of 3 because I need to make it all the way over here to get to NetZ. Whereas for NetV, I only need to go through 2 subnets to get to that one. So subnet visit count is the reason why you might want to. This might be a bit of a stretch, but it serves the point to make an example. We're going to define a sample default adjacent cluster table. Remember, the default adjacent cluster table is used when you've got alias searching. And we can make a couple of assumptions. We can either assume that whenever we have an alias search, we only want to search our own network, because I've already predefined everything cross-network as a CD or a C, and so all of those searches should be network qualified, and I should pick a different table than my default table. So instead, the first example here is all the searches for non-native APPN resources use network qualified real names, so we would never be using the default table to search for something outside our network. Instead, we would only, whenever we got an alias search in, we would always assume that the resource we're looking for is somewhere inside our network. And so the default table for A1 would simply have A1's name in it. That's the way I force the search of my own network. Now, if you have at least some searches for non-native resources, we'll use alias names. If at least some alias searches represent resources that are outside your network, well now you actually have to code a default cluster table that allows you to search maximum scope. You have to be able to search everywhere. And so you would basically list everybody that A1 knows about. All the non-native adjacent nodes and all the native border nodes, which in this case would be A1, C2, A2, A3, and A4. That's what BN equals none. The alternative is that you could code an adjacent cluster table that basically says BN equals full and just code one name in there as a placeholder, and now basically whenever you're doing it, you're doing a full search. Again, I do not recommend BN equals full. I would recommend using the previous chart where you're predefining everything as a CD or C so that all non-native resources are fully qualified searches. Alias searches are treated as native searches only, and you basically don't need to do any of this trial and error searching at all. So those are your two examples of sample default cluster tables. All right, so now I've been through all the APPN border node tuning sections. Now I'm going to give you a couple of hints on debugging searching problems. The worst one, of course, is resource not found. I've searched everywhere in the world and resources was not found anywhere. So let's talk about what we can do. We have invented quite a few start options over the years. We've added some of them very recently. They're called SIRF message start options for session initiation request failure message. There's usually a qualifier at the beginning which tells you what we're actually trying to, what kinds of session initiation failure messages we're actually going to display. I group them into two cases. The first three up here are knobs that turn on and off the messages in general. The bottom three down here will add supplemental information. As long as one of these controls were already in place, this can add supplemental information to the display. If you get to resource not found conditions, or if you find the resource but somebody else terminated it in the middle, you can get information about that. The most important one to me, of course, of these sub-options, if you will, is the FSIRF message. For resource not found conditions, enabling the FSIRF message start option tells VTAM, I want you to show me every search step that you performed, and tell me what sense code you got from it. If you couldn't find it, you must have gotten a sense code back. So I'd like to know what sense code you got back for each one. So if you turn on one or more of these controls, in conjunction with this control, then you basically will get detailed information about the searching that was performed. Now, up until recently, the only big master control you had up here was the SIRF message start option, which controlled searches that were kicked off by binds and CD inits and initiates. What it did not necessarily capture was any DJSLUST or direct search list searches that were performed through subarea networks. You would never get a message when a DJSLUST search failed. And what you find out is, in APPN networks, when nodes do broadcast searches, they reflect themselves into the subarea network with DJSLUST searches. And so if a broadcast search is performed and fails to find the resource, you don't get any messages with just the SFIRF message start option enabled. Instead, we added the DSARF message start option for DJSSCP, and that will basically say, even when you're sending a DJSSCP search through the subarea network, if you get to a resource not found condition, I want you to spit me, or a failure, I want you to spit out some messages for me and tell me what went wrong. Finally, we found out that wasn't even good enough because it didn't tell you what the APPN side of the node was doing. The SIRF message and DSIRF message start options only affect the subarea side searching for CDNets and DJSSCP. What we found out was we needed to know more information about what the APPN directory services component was doing. So we invented the LSIRF message start option. This is for locates. So now if you turn all three of these start options on, as well as the FSRF start option, and then you send a search out that doesn't work, then when the reply comes back, and you do this on all your hosts, then all your hosts will spit out messages about exactly what happened. And if you're not finding the resource, for example, because you're not searching far enough, or you don't have the cluster table set up right to do border node searching, you'll find out which node did not receive the search, which nodes did and did not search far enough. So that's what the next couple of charts are going to show you. So I took this network here, where basically it's all APPN except there's one subarea connection from 1A to 7 Baker here. I've got a casually connected end node, I've got a couple of central directory servers who are also border nodes that get me down into net C and net D down here. Right? And what I did was started a search on 1A for a non-existent application. And I wanted to see what messages I got out. And when I started a session for a non-existent application called Yoda, basically what you find out is that 1A says, sorry, I couldn't find him, and the only guys I searched was APPN, and I got not found back. And I searched that subarea CDRM 7 Baker and got routing exhausted back, which is basically not found also. And on 7 Baker, when that CDNet request came in, he said, oh yeah, I tried APPN, but I didn't have any CP sessions, so I couldn't do that. And I didn't send it back to 1A because 1A sent it to me, so that's all I could do. And what you find is, the only nodes who tell you anything at all about what failed are 1A and 7 Baker. You don't get to find out why. You don't get to find out if and why not these nodes or these nodes did not reach the search. And by the way, if you're looking at these side very closely here, I've got a character in the first column here that basically tells you which of the start options caused this message to come out. So this is the SIRF message and this is the FSIRF message start option. Those are the reasons these messages came out. So now, let's try flipping on the D and the L switches as well and try the same thing again. These are all the messages, in fact, not even all the messages, that we got out of just 1A. And remember, when you do searches like this, searches can kick off sub-searches, which kick off sub-searches, and the sub-searches actually clean up first, and then ours clean up second. So sometimes the messages actually come out in the opposite order that they're actually being performed. The first sets of messages to come out are the deepest, if you will. They complete first, and as we wrap back, we continue this thing out. But you can see, these are the steps that are actually being performed, starting with an APPN search, searching your end nodes, then the central directory server, broadcast from the CDS coming back in, ICN search, and basically I've shown you where on this chart you can see each one of these. But take a look, for example, at this piece right here. This is the APPN side piece of it when we do our APPN search. It tells me that I did a broadcast search to my served end nodes, which would be this guy, and it shows me that this guy here gave me a not found back. Then I did a directed search to my central directory server, which was 2A. 2A, when he was a central directory server, did the broadcast search, and when the broadcast search, it came in up here again. This was the broadcast search. And when it came into me, I did my local subarea search on 1A, but then I rejected it and spit out those messages. When it came back here, he went past the central directory server query and started the border node search. And from the border node search, he basically sent it to two peer border nodes, to AA and 2A. So you can see he actually made it there also. Notice also on these searches that it says the directed search was sent to this node and this sense code was set by that node. In all of these cases, you'll see the node that sent the sense code is the node that I sent the search to. But there are cases where I might be trying to send a search across the network and some node in the middle fails it for some reason. In that case, it would say, I'm trying to get the search all the way out to that node, but some node in the middle sent this sense code. So it actually tells you not only what node you were sending the search to, but also which node didn't like the search. You can also see that what happens when the search request came into 2A. When the request came into 2A, the first thing we did, it was a border node search, by the way, that came in. So we did our alternate, it was a central directory server search that came in. So the first thing that I did was query my alternate central directory server, which would be AA. And then I did a broadcast search of the network nodes. Remember, the central directory server's responsibility to do the broadcast search. search the local subarea side of my node. I do directed searches for my serial ICN search, and when that fails, I basically wrap it back up again. So now you can see the central directory server gets the CDS search, queries the alternates, sends the broadcast, searches the subarea network, searches the ICNs, and basically does EBN searching afterwards. But he does that as the origin border node. He has to wait until he gets the peer border node search rather than the CD server search for that. So down here, it's where we got the border node search request in, did a local subarea search, but then also did his search across here to this guy. So you can see that NetC got the search. You can see on AA that he got the alternate CD server search in. He saw the broadcast search also. And when the EBN search came into AA, he was allowed to search down to Bakerable. So you get to see that all these guys did it. The bottom line is, on this, even on Bakerable and Charlieable, these two guys down here, when the search comes in and flips over to the subarea side of the node, you actually get searches saying, guess what, the subarea side failed also. I got a search request from the APPN network, and it failed also, the local subarea search. So the bottom line is, from this display, I can tell that every node got the search, processed the search the way they were supposed to. If you find out that the search never made it down to this net ID, you can probably figure out what went wrong. You can see whether AA got it, whether his cluster table allowed him to go down. You can see whether he was allowed to go to his peer border node to get down there. You'll be able to look at the messages, hopefully, and be able to parse this out. Now, sometimes they're hard to understand because, you know, they come out in the opposite order. If you can't interpret them, collect the doc and send it to us. Guarantee, if a customer comes in right now and tells us, I can't find my resource, the first thing we're going to do is have you turn all these options on, all your VTAMs, and try it again, and then send us into system logs. Because we would much rather look at system logs than look at dumps to figure out how the searching stuff is going on. Second tip I want to give you is the display adjacent SSCPs command. A lot of people know that the display adjacent SSCPs command is used to display adjacent SSCP tables. Sorry, it's just about 5 more minutes, okay?
We can just resume here. Is that all 7 presentations?
Just 2 more, this one and search info. All right, so just let me try to finish it in 5 minutes and see if they can wait. Okay. So the next one I would like to talk to you about is the display adjacent SSCP CDRC command. A lot of people know that the display adjacent SSCP command will display your adjacent SSCP tables, but a lot of the times that doesn't give you a lot of information. This is a display of adjacent SSCP table that had just 1 entry in it. But this is a display of an adjacent SSCP table when I add the CDRC operand equals that node name to it. And what that does is says, I want you to take history and priority routing into effect. I want you to take dynamics into effect and add the dynamic entries and show me the whole list of things that you would search for this resource next time. It's not how I searched last time, it's how I'm going to search this time. So the bottom line here is that you see 2 extra entries being added to the table that were not in this table. That's extra information you didn't have by using the standard flavor of the command. These 2 entries came out because the first one is the learned or owning CDRM name, and the second one, because sorter was APPN from the start option, it basically added the IST APNCP entry to the table dynamically. So you get a lot more information by adding that piece. The last piece of information I want to show you is the display search info command, which basically shows you information about searches where we've sent the request out and have not received the reply yet. There could be a lot of other outstanding searches because sessions are queued and stuff. But in general, if you've sent a request out and not received a reply out, that looks like a hung search. The display search info command gives you information about hung searches. If you do display search info with list equals all, we'll show you all the OLU and DLU pairs, but we'll also show you the session ID. And if you do a display search info with the session ID on there, you get everything that you would ever want to know about that search. It shows you everyone we've tried so far. It shows you who we're waiting for from the subarea side's perspective. The APPN side, it'll also show you the who we're waiting for. In this case, the APPN search was concentrated behind another search that was already searching for the same resource. And when you look at that one, he says, yeah, well, I'm waiting for a reply back from that node right now. That's why I'm hung up. So the bottom line is the display search info command with the session ID operand can actually be used to tell you a lot about why a search might be outstanding. And so I hope this has given you some useful information as far as a practical guide to optimizing your APPN and EBN searching.